Swayam Prabha. Digital India. Educated India.
Hi, welcome back. So we had started turbulent 3D turbulent boundary layers, right? And I think we basically said that we looked at some of the equations, the basic equations for a 3D case, right? So and now we are going to look at, we're going to introduce, the turbulence into it, like we've done earlier, where the velocity will have a steady component and a mean component and a fluctuating component. So that way now, so the equations that we did last time, so we're going to sort of work on them and introduce the turbulence into them, right? Now, okay, so right, so now let us just go ahead straight up and say what are basically steady turbulent flow, right? So let us look at some equations. So we have steady turbulent flow. Okay, the momentum equation, steady turbulent flow momentum equations. So this equation is in the x1 direction. Now x1, x2, x3, just pull that up, and for example, so if you see here, okay, so this is the 3D boundary layer picture that we had drawn, right? So there's an arbitrary curved surface S, right? And we have x1 and x2, where we have free stream velocity components u1 and u2, right? And these are the velocity components these are the velocity components like in the boundary layer u1, u2 and u3 in these three axes. So this is the axis system, right, which is given like this. Okay, so this is the one that we're talking about. So going back here, so x1, right? So x1 u1 okay plus right okay 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 is equal to okay right. So basically what we're saying is that the velocity, right, component which we just saw here, so the velocity component here, right, this u1 will now also have a fluctuating component. This will have fluctuating component and this will have a fluctuating component, and that's what we are kind of writing out here. Okay, now the way we had set up the problem, okay, in that h3 turns out to be 1. Okay, so let's write that. So this h3 is actually equal to 1. Okay, so this is the equation we have. Let us write down the, so this is for, say, this is x1. Okay, so let's go and write that down in x2 direction as well. Okay, so x2, again, you can see here, del u2 del x1 plus u2 by h2. Okay, u3 again by h3 equal to 1. Okay, okay, minus k1 u1 u2 okay, is equal to minus rho h2 plus 1 by rho tilde x3 nu del u2 del x3 minus rho. Oh, yeah, well, and I forgot to do that. So, okay, so essentially, and when we do that in the x3 direction, right, when we do that in the x3 direction, what do we get? Well, we get the quintessential pressure equation. Right, so basically the pressure gradient in the x3 direction, which is x3 direction is essentially perpendicular, it's orthogonal to, is always orthogonal to every the x1 and x2 at every point in the at every location in the arbitrary surface S. Right, we've defined that earlier. Okay, that, and then let's also write down the continuity. Yeah, I think we can write down the continuity here, or maybe no. Okay, and then of course we have the continuity equation, right? So that is okay, so this is the continuity equations. So now we've used this K1 and K2, right? If you see, we've used K2 and K1, right? Let us write down what these are. Okay. Now K1, K2 are geodesic curvatures. Okay, of the lines x1 constant and x2 constant. You understand? So x1 constant, so you'll have lines where x1 is constant, right? And you'll have lines where x2 is constant, but obviously these lines are going to be curved on that surface, right? And these, so K1, K2 are geodetic, basically represents the curvatures of these lines, okay? So K1 is equal to minus H2 okay, and K2 Okay. So now here, if I may just sort of right. So lines of constant x1, right. So x1 is this, right. X1 is this. So what sort of line would we look at? Let's just say, so this is actually x1, right. X1 is constant over this. So something like that. So on that patch, x1 is constant. So right. So here, so k1 is the, so k1 is the geodesic curvature of the line x1 constant. So this curvature, right, this curvature is what is given by the k1, right. So similarly, x2, so this is constant, x2 constant. So lines x2 constants are on this surface, which are basically orthogonal to x1. So then the curvature of those lines, right. So we can sort of, so these lines, I guess, you know, lines like that. So these are where x2 is constant, right. Here it has, on this line it has one particular value of x2, another particular value of x2. Okay, fine. So that's what we understand by x1 constant and x2 constant. So curvatures of, so our geodesic curvatures of these lines, and it's represented in this fashion. Okay, and of course we've also we've just seen this, right. So let's just use a highlighter, I think. Yeah. So we have this turbulent stress component is right there. Turbulent stress component is like there, right. So and that's the place we use U3 dash, right. Okay, so we're trying to get some equations into place. So you can see I don't have a component which is varying with time. So therefore, this is, you know, why not? Well, just to make it, I guess we're trying to do things, you know, easier. That's all. No other conditions. I mean, in the sense, is there a question that turbulent boundary layers cannot be unsteady? No, of course they are unsteady. But, you know, right now I'm developing the equations for steady turbulent flow. As it is, it's kind of complicated. Okay, I'm trying to set that up. Okay, so we have the momentum equations. We do have, see, the way we are proceeding with setting up the equations is similar to what one would do for a laminar case also. Right? You set up the basic equations, and then you say that the pressure, you know, doesn't vary in the, you know, perpendicular direction, and hence del P del X is 0 in the y direction. So, and then of course, you know, the v component, that component of velocity in this case is the U3 component velocity is much you know, smaller compared to the other, and the derivatives are also you know, can be neglected in the x3 direction, and so therefore we come up with the you know, equation, right. So we come up with the equation which is this. So that gives us that. So finally, from that particular equation, so you can take one of these equations and look at it, right. So it would have del U3 del x1 del U3 del x2. So these are terms. So U3 is actually you know, very much smaller compared to the other one. So these terms will not be there. Okay, and so finally, when we work this out, and derivatives, you know, this derivative in the x3 direction is also going to be minuscule. Okay, so it boils down to the fact that the pressure in the x3 direction is essentially 0. Okay. Now, so we're doing the same thing. So now, however, what we do, because still the concept of boundary layer hasn't changed. Okay, so when you do the boundary layer and you come up to the edge of the boundary layer, so that's where you're meeting the free stream, right? So that's when you say that, okay, now what you start equating the pressure, right? So, so pressure gradients have to be related, therefore, to the velocities of the free stream, right, at the edge of the boundary layer. So in this case, we have two components of the free stream, which is U1 and U2, right? We saw that. Okay. So here we have essentially two components of the velocity. One is U1 and one is U2. This is the free stream. Okay. So, let us just say, so pressure gradients are related to the velocities u1 and u2. These are basically free stream, right, at the edge of the boundary layer. So, when I do that, u1 okay, minus right. So, we have two directions in which we have velocity components of the free stream, right. That then the other one is 1 by okay. Right. So, now this is the connection of the pressures. So, this is essentially the okay. This. Okay. So, the pressure gradients. Okay. Now that we have set this up, let us just take a quick look at them. So, this is our equation set up. This is our equation set up. When I say take a quick look at it, but I mean look at it, look at each term, what do they have? They have derivatives, right. We have the k1 and k2, which we know what they are. Okay. So, and we have these mean components of the mean value. This is the stress tensor, which has components from u3 as well. Okay. The fluctuating components, these are the fluctuating components. Okay. All right. So, this is what we have. Ultimately, when we are setting up these equations, we need to solve them. So, we need to figure out, okay, so what is at stake? What are the equations? What are the unknowns? And how do we go about it? So, that is why we kind of trying to have a, this is the continuity equation. Okay. So, that is the continuity equation. Okay. And then you have the pressure gradients. So, this is all kind of set up. Okay. So, now inferences. So, let's just say, sort of what inferences can we make from here and what calculations can we make from here. Let us see. Okay. So, I am going to write down this. Okay. Number one, in order to solve these equations, okay, we need to know the free stream velocity. Okay. So, u1 and u2. Now, having said that, right, there is no guarantee that potential theory can calculate these accurately. Okay. So, that is one of the things. We need to know the velocity but having said that, there is no guarantee that potential theory can calculate these accurately. Okay. So let's just say we assume the pressure is known. Okay. So the pressure is known. So essentially, if I go here, so the pressure is known. Okay. So del P, let's just say that we should be able to, this is known. Okay, let's mark that up. Okay. So let's just say, so del this term, this term. Okay. Right. So this is known. Okay. Say this is known. Right. Now, how many unknowns do we still have? Right. We have 5 equations. 3 governing equations. Right. 3 governing equations here. So how many unknowns do you think we have? Okay. How many unknowns do we have if you look at these equations? So the unknowns, one is this u1, the other is, let's just say, u2, right, and u3. So u1, u2, u3. So in each, actually, if you look at this, right, so the first 3 terms, in the first 3 terms itself we have the 3 unknowns, right. So u1, u2 and u3. So you have these 3 terms are unknowns. What else? The highlighted terms are also Reynolds stress. These are also unknowns, right. So these are all unknowns, and well, these 3 the Reynolds. So essentially, so what that boils down to is that is known. We still have 3 governing equations, right? Five unknowns, right? We have 5 unknowns, and these unknowns are essentially, okay, so well, I can sort of write those down here. Let's just write them down. So there are u1, u2, u3, then u1, u3, the stress tensors. These are the 5 unknowns. Okay. Now, these 2, well, they rely on empirical. Okay. So we're just trying to take stock of things, right? Because now is the time that I've set up the equations, now we're going to solve it. Now we think, but given the scheme of things, we just can't go ahead and solve them. We just, too many. So that's why we're trying to see what we can do. Okay. So as it is, 3 governing equations, 5 unknowns. These, of course, it relies on empirical info, right? Now, law of the wall, if you remember, right, which we have tackled so far in this class. Okay. So this law of the wall is simply very difficult to formulate in a 3D flow. It's as simple as that. Okay. So law of the wall, okay, is difficult to formulate in 3D flow, and the law of the wake doesn't seem to be valid at all. Okay. Does not seem to be valid at all. So what do we do? So this is the stuff, right? So here the thing is that so law of the wall, law of the wake is something that we've just done for a turbulent boundary layer. But what we're talking about here is a 3D case. And what we see is that for the 3D case, right, it is very difficult to formulate, and the law of the wake doesn't seem to be valid at all. So let me specify for 3D flow, right. Then what is the solution, right? So solution is twofold. So now we figure out that how we will solve these equations. So how we will solve these equations? Okay, so let's just say the solution then. Okay. Okay. So if you look at the you have the continuity equation, right? We have the continuity equation. So we can essentially eliminate U3 using continuity. Okay. So essentially what we'll do is we'll eliminate U3 using continuity, right, and B, integrate across the boundary layer. Yeah, like we do integrate across the boundary layer, right, in so that's it. So we eliminate U3 using continuity, okay, and we integrate across the boundary layer in x3 direction. Okay. So if we do that, right, then this results in two equations. Interesting, right? So we have three governing equations. Now if I do this, then this results in, so this essentially, so this means now this then results in two equations. Okay. What are those? Okay. Plus H1 plus okay. Okay. This plus K1 I will write out the definitions of this in a bit, so please bear with me, okay? U2 right, so that is the one equation. I think a legitimate question that one could ask me is that why are you writing all these equations and things like that? Because I think somewhere down the line you need to understand where equations come from. Okay, they look pretty scary and pretty exhaustive. They are, but then they're not meaningless. Each term has a meaning, right? And I hope by this time you know what each term means, and physically it has a meaning. And one more thing is that I think a big chunk of students, they think that if you just press the answers button, answers software, what you get, and then that's it. And then they just plot some things and come and talk about it. But I think that unless and until you really it's a great tool to have, it's a great tool to have, but then to use it and to understand it and to properly give it its due and also value it. I think one really needs to understand that all of this has been coded in somewhere, or you're using it in a numerical sense. This whole business is about how can we solve this, So I think it's very important, especially for troubleshooting, if you really don't have an idea of what exactly are you even solving, So I think it's also important to see that. And of course, if you are somebody who wants to code and do things, I think you should. Okay. All right, the second equation. Del x2 okay, minus k1 this, right? And then now I will write out, the theta and the other values. Okay, let me go to another page and do that. So where v square is equal to right. So essentially, we are taking the two components x1 and x2, right. So the mean component. I mean the resultant component, okay, that comes from there. So that is your v, okay. Then, and I think we'll try to understand this also, okay. So when I write out equations, right, then we try to understand this. So v delta 1 star u1. Okay, so what does this right hand side integral mean? Okay, so there is the deficit in the so essentially u1 minus, so when this is at the at delta, when it is height delta, at that time this is going to be nearly 0, because that's when you reach that 99% of the free stream. So we would expect that to happen here as well. So basically we're saying, so that's why we said this delta 1 star. Okay, so velocity, so you take that the deficit velocity, right, and you are actually sort of summing that up, right, into in that x3 direction. Okay, so to understand this, so if I were to sort of so let's just say this is your x2, right, and this is your x1, right, and then of course this is your x3, right. So in this case, you have this velocity which is right. So if I'm going to talk about, so let's just say that this is my boundary layer. This is my boundary layer. Okay, so this height is actually, okay, so here in this delta that I'm talking about is here. This is the delta that I'm talking about. Okay, so this is dx3. So dx3. So you actually have, so in dx3 is an element in this direction, right? So that means that there is a little difference, right? There is you could take an element like that. Now really, so if I were to take it at the, so, right? So you take the small heights from here to there and you take these. So then the deficit, so here it is U1, of course, right? This direction, this is the free stream, right? This is the direction. So this is, here it is, so here of course it is U1, and inside here it is small u1. So that is the deficit. Okay, and you kind of take those small values and multiply by x3, right? So this is what it means. So this is what I'm trying to understand here, that what exactly is what exactly is going on here. Okay, then the next one is, so now I think now we can guess. So the next one is basically V delta 2 star. Okay, so this is 0 to delta U2. Yeah, so maybe you should be able to, so now this is what the picture that I see is here. The picture that I see is for the x1 direction. Now you will have to draw the in the x2 direction, right? So why don't you sort of do that for yourself. Okay, then v square theta 1 1. Also, it should give you an idea in the sense that if you should know that how we calculate the so delta 1 star is a displacement thickness, right? Displacement thickness. So what do you, so if I were to just kind of briefly tell you what displacement thickness is. So displacement thickness is actually the distance by which the flow has to displace in order to, because of the existence of the boundary layer. If the boundary layer was not there, then it would just move past whatever surface it is flowing. But now, since there is that boundary layer, a little bit is going to push away from that solid surface, and that how much it is pushed away is the displacement thickness. So we are actually calculating that here, if you see, right? And in order to, right, so therefore this delta 1 star is actually displacement, so this one is equal to this whole thing divided by v, right? So v of delta 1 star, okay, is this. So so velocity, right, into the displacement, right? And so if you see the total velocity, right, of u1 and u2, right, so that is actually displaced, right? It's basically delta 1 star is that displaced, and I go into the boundary layer and then I see basically this is the deficit, because u1 here, there's going to be a profile, right? It's not same, that's why it's a boundary layer. So therefore, the difference between the free stream and the local value of the x1 component of the velocity. So this is what, so this is the reason why it will, this is the total value of it, okay, 0 to delta. Okay, so if you want to look at it that way, or sort of start with that and develop, and you can come up with this equation on your own expression, right? The same way that you do for a laminar boundary layer. Okay, so v square theta 1 1 is again. So now if you see, if you remember, so okay, I forgot to write the delta 3. So theta is actually representing momentum thickness, right? So and momentum thickness is again when you have the displacement, right? There is also mass displaced, hence there is displacement of momentum also. And how much thickness is that, right? So the point is, when the flow comes in, right? When the flow comes in, it is essentially just u1, right? Then u1 meaning the capital U1, and then when it goes on the surface, then it becomes small u1, right? Now, so I think, okay, I'm not going to get into details of it, but this is how you calculate the displacement thickness and moment thicknesses, okay? And then you see that if I just take the same height, if I just take, same delta on both sides, on the entrance and the exit, I'm not going to be conserving my equations of continuity of momentum, right? So I need an extra height, because now what was coming in as the capital U1 has actually become small u1. So I need to take that extra height. What is that extra height? That is this u1 minus u1, this first one, right? But then this u1 is not a single value, right? That varies in the y direction, and hence we integrate that from 0 to delta, right? So that is, therefore, that is the displacement thickness, okay? So similarly, I can write this as do I have anything here? Well, actually we don't have that. Why? Yeah, so we have only in two directions, so free stream. So, okay, so then, yeah, so v square theta 1 1. So now if you see, this is the same thing again, right, delta. So you just multiply it by the mass by the velocity, right. So essentially what we could have done is, if you just put a rho on the left hand side and the right hand side, then it will make total sense, okay. Rho is density, okay. So u1, again, see this, so then you will get the mass, right, you get the mass, and then to get momentum you multiply this by the velocity, this is this, okay. Then v square theta 2 2, okay, okay, is also equal to u2 minus this x3, right. So essentially I think the way you can look at this, okay, I'm trying to make as physical as possible. So you actually have, so if you see, you have this system here, you have x1 and you have x3, okay, and on that you have a certain velocity like that, and on the other thing again you have x3, right, and say this is x2. So here also you have the boundary layer, right. So we are looking at so that the point is, but then this is one surface, so essentially this whole thing should actually come here. So as you can see that if I integrate this, actually an entire boundary layer over this surface, right, which varies in both directions, which is what we're kind of trying to study here. Okay. So similarly, if you look at this, so theta 2 2 is actually this momentum thickness for this case. So I can basically say that this one is the momentum thickness, right, for this, right, and this one the momentum thickness, of course, for this, right. So again, for this one also, this is the displacement thickness, which is for this, and this is the displacement thickness for the second case, right. So you can see that, okay. And then finally v square so this is the cross, right. So basically now there is also a thickness, there is momentum which is basically getting transported, or which is being sort of shifted between from in the xy plane, and this is kind of taking care of that. Okay, and that has to be there, of course. So this and v squared theta 2 1. So this is an additional thickness which you do not get in a 2D case, or the boundary layer typically what we have dealt for so far. Okay, u1. So this is u2 minus 2d x3. Okay, so if you see here, okay, so u2 minus u2, so which is this picture, right? This picture. So this u2 minus u2, it is basically this picture. But the point is, as you move in the, so x2, right, x2 is fine, but you move in the x1 direction. X1 direction, this is going to change, and how there is going to change, which means that there's going to be a momentum transport, and this is going to be transported with what velocity? With u1 velocity, because you're going to move in the x1 direction, right? Isn't it? So this whole thing, you can think of this, you can think of this, for example, let's just say. So let's just say, you have this thing, right? So you place this on here, right here, isn't it? You place that, and then you keep moving it, right? You keep moving in the x. So this is what the plane is, right? So what I've sort of shaded is actually a plane which is going to land right up there, which is then their origin of coordinates also will be at the same point. Okay, right. So this is what now. So now we've come down to this. So we're trying to sort of this thing. So what we were thinking of how we're going to solve this and things like that. Okay, so we looked at this. So we said, what do we have to do? So we are doing this integral theory. So finally, we'll make this comment and stop for today, which is that the 3D integral theory. So let's just say, so finally, so 3D well formulated integral theory . Okay, so it's not easy. Okay, okay, we still have to solve PDEs. Okay, and we still have to solve PDEs. Okay, we're going to stop there. So what we will now talk about for a couple of classes is basically the integral theories and what we will do, because the point is why integral theory is not very easy. We understood this, right? You understood this, that when I wrote this down, so this is how the displacement thing, you understand that. But what is the difficulty? The difficulty is, how do I know the profile? How do I know the profile of the small? So as is, we wrote down earlier, even we are not sure that the potential theory can calculate the free stream components. But let's just sort of overlook that. But this at least has to be predicted. I mean, we don't know, right? How do I know that? So although this is kind of making sense to me, right? There is a momentum transport in the plane, and etc., etc. While all this is making sense to me, but then again I go back to the root problem that I don't know the velocity profiles within the boundary layer, whether you take this one or the other one, right? So we'll do exactly that, and we will figure out what possibilities are there, and essentially what can be done, some power laws, etc., etc. So let us see what we will do. So we'll look at some simple formulas, and I mean the next thing, how we can do that. So therefore this is the integral theory that I'm talking about, and it's not like we say we still have to solve PDEs. Okay, so I'll stop for now, and we'll take this further next time. Okay, thank you.